Okay, two more examples. Finding increasing, decreasing relative max mins using the first derivative table. Page 186, number 30. There's your function. Raise to the 1/3 power. Get a decent picture on your calculator. Looks like it's increasing the whole way. Question becomes, does it become perfectly vertical right there? If it does, then the tangent line actually goes through the curve. It has undefined slope. So the value of the derivative should be undefined there. And it looks like it's at 3. Take the derivative, use the general power rule, 1/3, base, reduce the power by 1, chain rule on the base. The derivative of x minus 3, 1. Simplify this, remove negative exponent, 2/3 power in the denominator, 3 moves to the denominator. This function is never equal to 0 because the derivative is never equal to 0. The original function is equal to 0 at 3 minus 3. But the derivative is never equal to 0 because the numerator is never equal to 0. So now I say, okay, let's find where it's undefined. Take the denominator, set it equal to 0, just the denominator. Divide both sides by 3. Now you have this power to undo the 2/3 power raised to the 3/2 power. Because power raised to a power, multiply the exponents, you get 6/6, which is to the first power. Whatever you do to one side, do to the other. Solve and get x equals 3 is where the derivative is undefined. So that's your critical value. And that's it. Make a first derivative table. Make a column for 3. Interval from 3 to negative infinity. Then from 3 to infinity. Find the value of the derivative. Now you can do this on your calculator. Go to y equals. Type in the derivative. Right there. So there, that guy. 1 divided by parenthesis 3x minus 3 raised to the 2/3 parenthesis for that. And then go to your table, look at the values to the left of 3. Doesn't matter which one you pick, these are all positive. Then go to the right of 3. So you can see to the left of 3, values are positive, undefined at 3, and positive again. These are the values of the derivative at these x coordinates. Okay? So the derivative is positive, then undefined, then positive. When derivative is positive, function is increasing. At x equals 3, the value of the function is 0. It then goes to increasing because the derivative is positive. So function is increasing, value becomes 0, and it continues to increase. So since the derivative is undefined, this is a vertical tangent line. Last one, number 36. Fraction, rational function. Use the quotient rule. So as Austin would say, low d high minus high d low, all over low squared, and away we go. Simplify, simplify. So here's your derivative. So I need to know where it's equal to 0 and also where it's undefined. Fractions are equal to 0 where the numerator equals 0. So I end up getting x equals 0 and x equals -8. Set the denominator equal to 0 and get 0. So this is where the derivative is 0 and this is where the derivative is undefined. Now you get x equals 0 in both of these. So where it's undefined is the one we want to use. So you have critical values at -8 and at 0. Now if you go back to pre-calc and you want to graph this guy, highest power in denominator, horizontal asymptote on the y-axis. This is equal to 0 at 0, so vertical asymptote. Alright, so this guy on this side is coming like this. Now what's happening at -8 is it looks like we're going to have a horizontal tangent line. We are going to have a horizontal tangent line. So this guy must be coming down like this, maybe crossing like that, and then coming back up and leveling off. And like right there is -8. Because we have to have that horizontal asymptote, and we have to have that right there. And on the other side, it just looks like it's coming down. This must be that -4 right there. And that's the only place it crosses. So this doesn't even cross again. It goes like that. And then comes back towards the axis. Okay, and levels off. So it crosses at -4. Dips to its min at -8. And then comes back up and levels off onto getting closer and closer to the x-axis. And then this side doesn't cross again, so it's just kind of uneventful. Comes over here, goes like that. So that's, now you have algebraic tools that allow us to find these guys analytically. Okay, so now I want to find the value of the derivative. Now what I know is that at -8 the value is 0. At 0 the value of the derivative is undefined. All right, now I just want to plug in numbers on either side. So here's the derivative, -x² minus 8x -x². Shoot, did it again. Parenthesis -x² minus 8x divided by x. Don't need that set of parentheses, but you gotta be kidding me. -x² minus 8x parenthesis divided by x raised to the 4th. Not that hard to do. Alright, so second table, look for a number to the left of -8. These are all negative values. Look how close they are to 0. That's that function. This is the derivative. So these are all negative. So derivative. Now notice when you describe, you're walking left to right. So this function is decreasing. Now after -8, two times 10 to the -4th 0.0002. Positive. There's no negative sign in front of these. So these guys are positive, which means function increasing all the way, all the way. Now I want to get a positive number. So let's see, second table set. Let's start at like 10. Go to my table. These guys are negative. Derivative negative, function decreasing. See, so derivative negative to positive, function decreasing to increasing, down to up gives you a relative min. Derivative undefined, you could have a corner, but at 0 the original function is undefined. Okay. This is up to down, but they don't meet, so that is not a relative max. There is no corner or smooth spot there, so it's nothing. Just leave it like that. Okay, cool. So you now have the pre-calc stuff where you can get the horizontal and vertical asymptotes, holes if we wanted to, roots. So I should have, when I shouldn't have drawn that, I should have realized that first. And then now we can use calculus to algebraically determine increasing, decreasing relative max mins. All right, so I'll post this video and then I'll post some problems to do, and hopefully I'll talk to you tomorrow.